Welcome to the Insightful Professor. In this lecture, we will examine the workings of the denial of service attack. Because this threat is one of the most common attacks on the internet, it's prudent for computer users to understand how it works and how to defend against it. Consider that if it's easier for sources to generate service requests than it is for a server to check the validity of those requests, then it will be difficult to protect the server from malicious requests that waste the resources of the server. This creates the opportunity for a class of attack known as denial of service. As we talked about fundamental security objectives for data and for information and computing services, we identified three security objectives for information and information systems: confidentiality, integrity, and availability. In our earlier discussions, we mentioned attacks that largely considered confidentiality and integrity. With a denial of service attack, the concern is availability. The NIST standard identifies confidentiality, integrity, and availability as the three security objectives for information and information systems. These three concepts embody the fundamental security objectives for data and for information and computing systems. With confidentiality, a loss of confidentiality is the unauthorized disclosure of information. With respect to integrity, a loss of integrity is the unauthorized modification or destruction of information. And finally, availability. A loss of availability is the disruption of access to or use of information or an information system. This is what we want to consider as we examine denial of service attacks. Availability then relates to a system being accessible and usable on demand by authorized or legitimate users. A denial of service attack is an attempt to make resources unavailable to its intended users. It's a general attack category in which access to network applications or data is denied to intended users by overflowing the buffer or consuming resources such that there are undue delays in accessing or using data. As an example, consider the idea of flooding a web server with so many spurious requests that the server is unable to respond to valid or legitimate requests from users in a timely manner. With SQL injection, we considered briefly a form of denial of service. We explained how a query against a single table could be changed to produce what is called a cross-join or Cartesian product involving a very large table. Considerable system resources would be affected by the processing of this query. Here we provide the definition from NIST of denial of service. We distinguish this form of attack on availability from other attacks that cause damage or destruction of IT infrastructure and consequent loss of service. This attack does not even attempt to intrude on a system or to obtain sensitive information. It simply aims to prevent legitimate users from accessing the system. This type of attack is fairly easy to execute. The basic concept requires a minimum of technical skill. It's based on the fact that any device has operational limits. In the context of computer and communication security, the focus is generally on network services that are attacked over their network connection. From the NIST definition, it's apparent that several categories of resources could be attacked. The term bandwidth generally refers to the transmission capacity of a connection. we consider it to be the maximum rate of data transfer across a given path. Network bandwidth relates to the capacity of the network links connecting a server to the internet. For most organizations, this is the connection to the ISP, the Internet Service Provider. Usually, this connection will have a lower capacity than the links within and between ISP routers. This makes it possible for more traffic to arrive at the ISP's routers over these higher capacity links than can be carried over the link to the organization. When this situation occurs, the router must discard some packets, delivering only as many as can be handled by the link. In normal network operation, such high loads might result from a popular server experiencing traffic from many legitimate users. A random portion of these users will then experience a degraded or non-existent service. This is expected behavior for an overloaded TCP/IP network link. In a denial of service attack, most of the traffic directed at the target server is malicious, generated in some way by the attacker. This malicious traffic overwhelms legitimate traffic, effectively denying users access to the server. An attack on system resources aims to overload or crash the network handling software. An attack on application resources typically involves several valid requests, each of which consumes significant resources, thus limiting the ability of the server to respond to requests from other users. A denial of service attack that targets system resources takes a different approach. Rather than consuming bandwidth with large volumes of traffic, specific types of packets are sent that consume limited resources that are available on the system. These resources can include temporary buffers used to hold arriving packets, tables of open connections, and similar memory data structures. The SYN spoofing attack targets the table of TCP connections stored on the server. Another form of a system resource attack uses packets whose structure triggers a bug in the system's network handling software. The result is the system crashes. As a result, the system can no longer communicate over the network until this software is reloaded. This is achieved generally by rebooting the target system. Such packets are referred to as poison packets. The classic ping of death and teardrop attacks were directed at older Windows systems. They were of this form. Poison packet ping of death and teardrop attacks targeted bugs in the Windows network code that handled ICMP echo request packets and packet fragmentation, respectively. TCP packets are of limited size. In some cases, simply sending a packet that is too large can shut down the target machine. This action is referred to as the ping of death. It works simply by overloading the target system. The hacker sends merely a single ping. This packet is very large and thus can shut down some machines. The only real safeguard against the ping of death is to ensure that all operating systems and software are routinely patched. This attack relies on vulnerabilities in the way a particular operating system or application handles abnormally large TCP packets. A feature of TCP/IP is fragmentation, which allows a single IP packet to be broken down into smaller segments. Sending a ping packet larger than 65,535 bytes violates the Internet Protocol. To exceed this size limit, an attacker would generally send malformed packets in fragments. When the target system tried to reassemble the fragments, it would end up with an oversized packet. This resulted in a memory overflow and led to various system problems, including a system crash. Ping of death attacks were particularly nasty because the identity of the attacker sending the oversized packet could be easily spoofed, and because the attacker didn't need to know anything about the machine they were attacking except for its IP address. In the teardrop attack, the attacker sends a fragmented message. The two fragments overlap in ways that make it impossible to reassemble them properly without destroying the individual packet headers. When the victim attempts to reconstruct the message is destroyed. This causes the target system to halt or crash. There are a few variations on the basic teardrop attack that are available, such as Teardrop 2, Boink, Targa, Nestea Boink, New Tier, and Syndrop. We've mentioned Ping. Ping is a common network utility used for diagnostics. The utility is used to test connectivity to the specified destination. It sends TCP ICMP echo request packets to the destination and measures the time taken for the echo response packet to return, if it returns at all. Usually these packets are sent at a controlled rate. However, the flood option of the ping command specifies that they should be sent as fast as possible. ICMP is the Internet Control Message Protocol. It's used by hosts and routers to communicate network layer information to each other. The most typical use of ICMP is for error reporting. For example, when you run an HTTP session, you may have encountered an error message such as destination network unreachable. This message had its origins in ICMP. At some point, an IP router was unable to find a path to a host specified in the HTTP request. The router created and then sent an ICMP message to the host indicating the error. Looking now at application resources as the target of an attack, we say that an attack on a specified application, such as a web server, will typically involve several valid requests. However, each of these requests consume significant resources. The consequence is that in tending to addressing these requests, the system is limited in its ability to serve or respond to additional requests by other users. As an example, consider a web server that might include the ability to make database queries. An attacker could generate many large, costly queries that severely load the server. This limits the server's ability to respond to valid requests from other users. Such an attack is known as a cyber slam. An alternative is to construct a request that triggers a bug in the server program with the result that the server crashes. Then the server is no longer able to respond to requests until it's restarted. Denial of service attacks may also be characterized by how many systems are used to direct traffic at the target system. Originally, only one or a small number of source systems directly under the attacker's control was used. This is all that is required to send the packets needed for any attack targeting a bug in a server's network handling code or some application. Attacks requiring high traffic volumes are more commonly sent from multiple systems at the same time, using distributed or amplified forms of denial of service attacks. Let's look at another classic denial of service attack, the ping flood attack. The aim of this attack is to overwhelm the capacity of the network connection to the target organization. If an attacker has access to a system with a higher capacity network connection, then this system can likely generate a higher volume of traffic than the lower capacity target connection can handle. The traffic can be handled by higher capacity links on the path, but packets are discarded as capacity decreases. The source of the attack is clearly identified unless a spoofed address is used. The consequence of the attack is that network performance is noticeably affected. Falsifying an IP address is referred to as a spoofing. With spoofing, packets seem to come from an IP address that differs from the address they really originate from. In a classic ping flood attack such as this, the source of the attack is identified since its address is used as the source address in an ICMP echo request packet. This has two disadvantages from the attacker's perspective. First, the source of the attack is explicitly identified, increasing chances that the attacker can be identified and legal action could be taken. Second, the targeted system will attempt to respond to packets being sent. In the case of any ICMP echo request packets received by the server, it would respond to each with an ICMP echo response package directed back to the sender. This effectively reflects the attack back at the source system. Since the source system has a higher network bandwidth, it's more likely to survive this reflected attack. However, its network performance will noticeably be affected, again increasing the chances of the attack being detected and action taken in response. For both reasons, the attacker would like to hide the identity of the source system. This means that any such attack packets need to use a falsified or spoofed address. In this example network, the attacker might use the web server of the large company to target the medium-sized company with a lower capacity network connection. Such an attack might use a flooding ping directed at the web server in the target company. This traffic can be handled by the higher capacity links on the path between them until the final router in the internet is reached. At this point, some packets must be discarded, with the remainder consuming most of the capacity on the link to the medium-sized company. Other valid traffic will have little chance of surviving discard as the router responds to the resulting congestion on this link. In denial of service attacks, it's common to find packets used in conducting these attacks that have forged source addresses. This is referred to as source address spoofing. An attacker with privileges to access the network handling code on a computer system can easily create a forged source address. Note that while we're talking about source addresses, it's also possible to alter other attributes of a package. The use of packets with forged source addresses means the attacking system is much harder to identify. The attack packets seem to have originated at addresses scattered across the internet. The way the attacker forges the source address is usually via the raw socket interface on an operating system. A raw socket is a type of socket that allows access to the underlying transport provider. The access needed by an attacker to change the source address is usually via the raw socket interface present on many operating systems. This interface was provided for custom network testing and research into network protocols. It's not intended for normal network operation. However, for reasons of historical compatibility, this interface has been maintained in many current operating systems. Having the standard interface available simplifies the task of an attacker seeking to generate packets with forged attributes. Note that if this interface was not available, an attacker would need to install a custom device driver on the source system to achieve this level of access to the network. The process would be much more error-prone and dependent on operating system version. In conducting the attack, the attacker generates large volumes of packets that have the target system as the destination address. The result of this excessive traffic is congestion in the router at the final lower capacity link. Because spoofed addresses are being used, the packets themselves do not reveal the identity of the sender. To identify the true source of these packets requires network engineers specifically query flow information from their routers. This is a manual process which takes considerable time. Backscatter refers to the reflection of waves, particles, or signals. In computer network security, backscatter is a side effect of a spoofed denial of service attack. Because the target machine cannot distinguish between spoofed packets and legitimate packets, the targeted machine responds to the spoofed packets as it normally would. These response packets are known as backscatter. Security researchers, such as those with the HoneyNet project, have taken blocks of unused IP addresses, advertised routes to them, and then collected details of any packets sent to these addresses. Since there are no real systems that are using these addresses, no legitimate packages should be directed to them. Thus, any packets received might simply be corrupted. But it's also the case, and more likely, that these packets are the direct or indirect result of network attacks. Monitoring the type of packets gives valuable information on the type and scale of attacks being used. This information is being used to develop responses to the attacks being seen. In our overview of computer communication networks, we discussed packet headers. These headers contain information used to guide a packet from its source host to the destination host. The headers also contain some signal bits used as flags that are turned on to indicate some type of communication. In general, a denial of service attack depends on sending malformed packets. This may be spoofed addresses, or it may involve these signal bits. In a normal network conversation, this begins with one side sending a packet with the SYN bit turned on. The target responds with the SYN bit and the ACK bit, which is the acknowledgement. It's basically saying, hey, I want to talk to you, and says, okay, yeah, I'll talk to you. And that's what we've got with the SYN and the ACK, beginning the conversation and coming to some agreement. The sender responds with just the ACK bit turned on, and then communication can commence. After a time, the original sender terminates the communication to say, hey, we're all done, and sends a packet with another bit turned on. This is the fin bit to indicate finish. So these bits play a significant role in normal conversations that occur in a network. Along with the basic flooding attack, the other common classic denial of service attack is SYN spoofing. The SYN spoofing attack targets the table of TCP connections on the server. This attacks the ability of a network server to respond to TCP connection requests by overflowing the table used to manage such connections. What this means is that future connection requests from legitimate users will fail. Thus, these users are denied access to the server. To understand the operation of these attacks, we need to review the three-way handshake used by TCP to establish a connection. To initiate a TCP connection between a client and a server, a three-way handshake is completed. The client sends a small TCP segment to the server. The server receives this, acknowledges it, and responds with a small TCP segment. The client acknowledges the receipt of this segment, sending that acknowledgement to the server. That's the third part. That's the three-way handshake. In addition, with the client's acknowledgement to the server, the client could actually initiate the conversation and send some data, part of the message, within that third packet. The first two segments carry no payload. There's no application layer data. There's nothing really being sent other than the initiation and confirmation of the connection. The third segment optionally can carry data. Once a TCP connection is established, the processes can then commence to transmit data between themselves. Here's a diagram that we'll walk through to explain the process. The client sends this special TCP segment to the server. There's no data in it, so that's part of what makes it special or unique. But the other thing that's special about it is one of these flag bits, the SYN bit. The synchronized bit is set to 1. This is what indicates the request to initiate a connection. So the client also will randomly choose an initial sequence number. That sequence number is included within this SYN segment. The server then receives this segment and allocates buffers and variables to the connection. So note that work is already being done on the part of the server, and we haven't even completed the three-way handshake to commence the conversation. This is an important point. The allocation of the buffers and variables on the part of the server prior to completing the third step of the three-way handshake is what makes TCP vulnerable to a denial of service attack known as SYN flooding. So the server sends the connection granted segment to the client. There's a SYN bit that is set, and there's an ACK bit, the acknowledgement bit. Again, this segment contains no application data. It contains three important pieces of information within the segment header, though, these flags being set. The SYN bit is set to 1. The acknowledgement bit is set to the client's sequence number plus 1, and the server initial sequence number. So notice that the client sends a sequence number. The server in the response kind of echoes that back, plus 1, but sends its own sequence number. So the server chooses its initial sequence number, puts it in the sequence number field of the segment header, the connection granted segment is saying, in effect, I received your SYN packet to start a connection and your initial sequence number. I agree to establish this connection. Here's my initial sequence number. Upon receiving the SYN segment, the client allocates buffers and variables for the connection. The client host sends the server yet another segment. This is the third part of the three-way handshake. In this segment, the client acknowledges the server's connection granted segment, puts a value of the server sequence number +1 in the acknowledgement field of the segment header. The SYN bit is set to 0 since the connection has been established. The third stage of the three-way handshake may carry client data to the server in this segment. The client then sends that acknowledgement to the server, and the connection is established, communication can commence. So what's the purpose of the three-way handshake? Well, the processes establish parameters of the ensuing data transfer. The sequence numbers are not just completely arbitrary numbers, but they play a significant role in conducting the subsequent conversation. Both sides of the connection initialize many TCP state variables, as we've indicated. Once a TCP connection is established, processes can then send data to each other. So those sequence numbers, the role that they play is this is what gives us a reliable data transfer. So TCP is considered to be a reliable protocol. TCP views data as a stream of bytes. Sequence numbers are over the stream of transmitted bytes and not over the series of transmitted segments. This is how we start to get that reliability. It's basically saying, well, I'm starting at some number, so the first byte that you get from me will be that number. The second byte will be that number +1, that number +2, and so on. And that's how the system can confirm that it has received the proper message. The sequence number for a segment is the byte stream number of the first byte in the segment. The acknowledgement number a host puts in its segment is the sequence number of the next byte it's expecting from the other side. And again, this is how we keep the two parties in agreement as to how much has been sent and how much has been received. So sequence numbers are very important within the three-way handshake and within the conversation as a whole. So what does a host do when it receives an out-of-order segment in a TCP connection? Remember from our previous video introducing concepts of computer communication networks, we talked about congestion and possible queuing delays and things of that sort, which could interrupt transmission of segments. So we could actually receive segment 4 before we got segment 3. So in this case, there are two choices. The receiver immediately discards out-of-order segments. The receiver, alternatively, could keep out-of-order bytes and wait for missing bytes to fill in the gap. Well, I know I'm expecting 3. I got number 4. Let me just put it over here on the side, and I'll wait for number 3. Then when I get 3, I can pass both 3 and 4 to the application. So the latter choice is more efficient in terms of network bandwidth, and this is the approach taken in practice. So many of the most common network attacks, including the incredibly popular SYN flood attack, exploit vulnerabilities in TCP connection management. In practice, this ideal exchange sometimes fails. These packets are transported using IP, which is unreliable. but it is best effort. I'll give you my best shot at getting it done, but there's no guarantee. So any of the packets might be lost in transit as a result of congestion, for example. Hence, both the client and the server keep track of which packets they have sent, and if no response is received in a reasonable time, will resend those packets. As a result, TCP is a reliable transport protocol, and any applications using it need not concern themselves with problems of lost or reordered packets. This does, however, impose an overhead on the system in managing this reliable transfer of packets. In this video, we introduced important characteristics of denial of service attacks. We noted that a denial of service attack addresses availability rather than confidentiality or integrity, as we saw in other forms of cyber attacks. Because the attack is often directed against network bandwidth or network handling software, we discussed some features of a network to provide additional background for understanding how these attacks occur. Specifically, we defined denial of service attack. We explained how these attacks might be conducted. We identified primary resources that would be the target of such attacks. We explained the concepts of source address spoofing. And we described how the TCP three-way handshake is used to establish a connection between hosts, and also how this introduces vulnerabilities. In our next video, we will continue our discussion of denial of service attacks. We will examine SYN flooding and SYN spoofing attacks, distributed denial of service attacks, HTTP-based attacks, and more. We'll also consider defenses against denial of service attacks. Hopefully you found this video to be informative and helpful. If you have any questions or comments, let us know. If you haven't already subscribed to the channel, consider doing so in order to be informed when we post other videos. And once again, thanks for watching.